Okay, folks, we're going to be looking at the concept of a uniformly distributed load. Now, this idea of a uniform load is a little bit different to what we've been looking at up until now, which was looking at point loads. So first of all, with our point load that we've been looking at originally, if we have a beam that's normally supported, could be a cantilever as well, doesn't really matter. The type of loads that we've been looking at have been point loads. So we might have 10 kilonewtons acting at that point right here on the beam, and we might have another point load of 15 kilonewtons acting at this point. They're acting at a single point. And quite often for engineering purposes, that is good enough, and quite a few of the calculations, certainly all the calculations you will do for your HSC for where you're doing a calculation for shear force, for your shear force diagrams, and also your bending moment diagrams. Will be all with this type of point load, okay? And you remember with this, you would calculate your reactions at your supports and for your shear force diagram, and I'm not saying this is exactly what this would look like, but you'd follow that force up, you get to the 10, then you come down, you go across, and you go back up 15, and you should end up back at 0 when you get here, and then you'd calculate your bending moment diagram, etc., etc., based on these areas. So we've done that to death, and we should be able to understand how to do that type of calculation. And please keep in mind that you will not be asked to do calculations involving a UDL, but you need to know what it is, and later on you're going to need to know what the shear force and bending diagrams, bending moment diagrams look like. But first of all, we need to describe what it is. So UDL is the acronym for what we've already discussed, which is a uniformly distributed load. Okay, it helps to actually analyze words. Uniformly is another way of saying evenly. Distributed is another way of saying spread. And load, of course, is a force, usually resulting from a mass on the beam. So we've got uniformly spread force, or uniformly distributed load. So for this situation that we were just discussing, if you have our normally supported beam, if you imagine a person standing there on the beam on one tippy toe, okay, his mass is going to be presenting a load force at that very point, and this is the very definition of a point load. If you want to use the same analogy, if this same person were to lie down on our beam and spread his weight evenly over the surface of the beam, he would become a UDL, or a uniformly distributed load. Now, this type of question, or this type of load, is normally designated in the textbook. You will see if you have your normal beam-like structure, and we might have a pin at this end and a roller at this end. Seems to be the most conventional way of supporting. You might see it designated like this, as these tiny little half circles going all the way across the beam, kind of show you that the weight is spread across the beam. And you would have a distance here, let's make it 10 meters. And then the UDL is expressed as a value that, instead of for a point load, you're just given a force, a single force, But for a UDL, you'd be given a force of, say, let's make life really easy for ourselves and say 10 kilonewtons, but it would be per meter, and that's the way you know that it's a UDL, because it's spreading itself out per meters. So as you go each meter across this 10 meter span, you're going to be adding 10 kilonewtons of force as you go across. Now, to calculate the actual reactions at the supports, it's handy to be able to convert a UDL to a point load force. And how do we do that? Well, it's really, really simple. We just take our UDL and we multiply by the distance that it's acting over. So for this situation here, we've got UDL, what a mess. We've got UDL equals 10 kilonewtons per meter. And we've got our length of 10 meters. So we just say point force is equal to 10 kilonewtons per meter times 10. And we know that 10 times 10 is going to give us a point force of, you guessed it, 100 kilonewtons. And the only other question you've got to answer is, well, where is it acting? And whenever you do your calculation over the distance that it's acting on, the section that the UDL is acting on, you would find that the actual point force is acting in the dead center. So you would have between here and here 5 meters, and between here and here 5 meters. So you know that that 100 kilonewton point force is acting at the center. And the only other thing that you would need to know then is, well, what are the reactions at each support? We know that it's because it's symmetrical that you would have 50 kilonewtons acting up here, and you would have 50 kilonewtons acting up at this support. And that's how you convert a uniformly distributed load to a point load. Pretty simple, huh? Watch this video and then watch the video under it. Then we're going to do some exercises involving converting UDLs to point loads and working out where they're placed on the beam. See you next video.